Hello.
Hey, what's up, Shumi?
Hey, here.
Ready for a retreat today?
Yeah, I guess. Still
You
preparing
figure out
like
who you're going to roast.
yeah, I kind of like have a sense of who I'm roasting, but it's just really hard to like come up with stuff, you know?
Yeah, that's true. You don't really like know the person that well to start off with,
Yeah.
but like there's a lot of good stories that people know about other people. So,
Yeah, I've been asking around.
I heard that you guys were going to go after Abby.
Maybe.
I'm gonna cut this from the recording, of course, but like I heard that he's gonna get destroyed pretty badly, so I'm very much looking forward to it.
I'm not doing him though. It's someone else doing him. Someone else is doing him. So
Yeah, I only know about that one guy, but I don't know anyone else who's getting roasted.
yeah. Well, I don't think I should reveal it just now, you know. We'll keep it as
Yeah, I like a good surprise as well. Hello.
Hello.
Hi. Where is everyone else?
It's Berkeley time, so we're just gonna wait like 10 minutes for them. Wait, were you guys told that the fundamentals was happening today at 2?
Yeah, I think Alexi made like this Slack post about it.
I see. Yeah, it's not at the normal time, so some people might not see it. Oh, cool. Do you guys see the blue lines on my screen?
Yeah.
Yeah.
This
We,
is so
we also
cool.
see the cats walking across your screen.
Oh yeah, do you know that you guys can do that for IPython notebook? It's so cool. It's like,
How do
How do
you?
you do it?
That's sick.
I completely forgot. I think it's in
Is that only in like Colab or is that anything?
it's only in Colab, unfortunately.
You
But the
know how
fact
to,
that they include it is like part of the reason why I love Colab so much.
Do you like connect to your local runtime?
I think this is a setting that you change for pretty much all of your IPython notebook. It's like a personal setting.
Yeah, I found out there's like a dark mode for Jupyter Notebook.
There's a dark mode.
Yeah. I think I should install them. So I was working on a project with someone and they were using dark mode. I thought that was sick. But then all the matplotlib plots look really weird because it's kind of like a PNG, so it's like more of a transparent background, so black text on like
Yeah.
gray.
Like blend in with the background. Right?
Yeah.
I think it's under settings in tools.
Sorry. Oh yeah,
Yeah.
there it is.
Yeah.
What's Colab Pro? That sounds sick. Wait, so if you do a matplotlib, does it look transparent then? Or actually, I don't know. If you want to put that in here.
Well,
You
this
would
is the
probably-
to-do code, so I can't really
Yeah.
run anything right now. But yeah, I guess we'll see what happens when you guys complete it then. Are you guys ready for retreat this semester?
Oh yeah.
So you're really insightful.
Yeah, like the part that I'm most looking forward to is the member roasts, and I heard that you guys were going to go after like Abi and some of the other officers, so I'm like really looking forward to it. I'm like going to tape this, put this on YouTube, try to get a couple 100,000 views. It's gonna be nice.
100,000.
Also, is this workshop being recorded? Because I might have to dip in like the last 15 minutes because I gotta drop off my sister somewhere.
Oh yeah, I think that's
should
being
be,
recorded
yes.
right now.
Recorded.
Okay, that.
All right, why don't we get started then? Since one more person had just joined us and it's birthday time. So today's workshop is on computer vision, so that the model is going to be seen 2020 in 2020, even if you don't want to. So the problem of computer vision is applied to numerous sort of tasks. For example, you can use computer vision for classifying what is within an image, and you can do things such as regression as well. let's say you're given a picture of a temperature probe and you want to see like what's the height, for example. I don't know. But the field of computer vision is like pretty widespread. And the task that we'll focus on for today is just going to be, if we have an image, can we detect and see what is within that image? So there's the agenda. So we're going to first talk about, well, you learned in previous lectures that neural networks work pretty darn well. Like we can throw a bunch of data at it, like the input might be a sine wave, and it will be able to successfully predict what the value for the sine wave for values it hasn't seen before. So it works super well. But when we take neural networks and apply it to images, it actually becomes like hot garbage. Like it actually doesn't work that well. It's like using an F-tier character. And we'll talk about why we want to potentially use a convolutional neural network instead. We'll go into how convolutional neural networks work. And then lastly, we'll go into some of the uses for CNNs, such as YOLO. All right, so we're giving a task here, which is if we have an image, which happens to be a cat burrito, we have to predict what it is. We should be able to assign very high confidence for labels such as, well, cat burrito, we have 95%. And for all the other things, such as shoe or toilet roll, can only be like 3% or 2%. So we want the model to be able to give us very high confidences. And perhaps one of the issues that we'll see later on is, well, let's say I were to take this image and I shift it over by a little bit. So you see this is the before image and this is the after image. Is this still a cat burrito?
Yes.
Yeah,
I
so
think
it's still a cat burrito, but all we've done is shifted over the image. So it should be able to tell quite well that it is. And let's talk about how, well, first of all, let's use a neural network first, right? So there's no big deal with using neural networks. In fact, it can work quite well in some contexts. And how we go about feeding a 2D image into a neural network that only wants a 1D vector. Does anyone have any idea?
We like take it layer by layer and then we stack.
Yeah, exactly. Exactly, layer by layer. So for example, let's pretend these red lines are like a line of pixels and not like a bunch of pixels. So let's say we will grab one line of the pixel, put it here, take the next row of pixels, put it here, and so on and so forth. So we have a 64 by 64 image. We end up with a 4096 vector, 64 times 64 vector, and we can feed this into a neural network and do classification. No big deal. Now, does anyone see any problems with this approach?
Yeah, if the arrangement of pixels with respect to each other matters a lot, and you kind of lose that because when you have like a 2D image, like it's like you're comparing stuff with the adjacent pixel. That's how you have like it's how you have an object, right? Because an object is not formed by one pixel. It's formed by many pixels arranging themselves in like a certain way. But you lose that when you turn it into a one-dimensional vector.
Yeah, exactly. That's like a very perfect answer right there. We lose this geometry. Like if I were to take this and just give you a line of black and white pixels, you probably wouldn't be able to tell that it's a cat. What might be another issue with using neural networks like this? So let's go back to the thing I was talking about before, where we take the image and we shift it over. And you should still be able to tell that it's a cat burrito. Does anyone see any problems with that? Would the neural network do well in this instance? So if we were to take this image, move it over by a couple of pixels, would the neural network still be able to give us a good prediction?
Probably not.
Sorry, what do you say?
Probably not.
And why is that?
Like let's say the neural network is trained such that, well, either it will not train because of the movement of the cats around the image, Or if we train it on a data set where the cats are always dead center of the image, if we off shift it by even a little bit, the features that we're feeding, the data that we're feeding into the network completely changes. Like the axes, they all change. It's expecting it to be in the center and it's off to the left. So the model can't really compensate for that.
Yeah, exactly. So, so this is the reshape image. So yeah, it is not, first of all, it is not translational invariant. So this is exactly what you said, where if I take this image and I shift it over by a little bit, so let's say blue is the new input, it's like this column right here that we added by shifting over the image. Now, if we look, each neuron gets a different value as input. So each neuron will get a completely different corresponding input. And as a result, your output will probably change dramatically. Now, like you said, if every single image is like dead center, then we might be able to do like all right. But the moment we shift over an image, we're like completely screwed. Yeah, and lastly, the last problem is that it loses geometry. Pixels that are close together, like this one right here, this one right here, are now completely separated. And we lose the geometrical sense of the image. Yeah. All right, so neural networks are really, really bad. And that's why we try to use something called convolutional neural networks. So this is a CNN, and we'll go into more detail about the animation that's happening in this image. But kind of what it's doing is that we have this kernel, or you can think of it like a mini neural network that's being split across the image. And furthermore, it's not doing like a row of pixels at once. It's doing this like 2D patch right here. Yeah, this 3x3 patch that is being fed into the mini neural network at each time step. And we're shifting it over one by one, and it's the exact same neural network. So with this new architecture, we're able to sort of fix some of the problems that we had before. Right? For the person who just joined, we're going to convolutional neural networks. We talked about some of the problems with neural networks being bad, like it's not translationally invariant. If I take the image, move it over, it would be a different output. And that if we were to do a neural network where we have an image, we lose the geometry of the image. Like we passing a 4096 vector, it would lose all geometrical sense of the image. And we're trying to fix it with convolutional neural networks. All right, and let's look at this in like more detail, right? So we have a 3x3 patch. So I'm gonna take it out and put it right here. And it's like -1, -1, 1, 1. And we have a kernel. So this is our mini neural network. We're gonna, you can call it a convolution or a kernel. I like calling it a kernel. And what it's doing is that it's doing a element-wise multiplication between the patch and the 3x3 vector, the matrix right here. And the task that we're going to be working on is classifying X's and O's. So exactly what is happening here. We have a kernel, we're doing element-wise multiplication. So how does that work, right? It's kind of like a mini neural network where we're taking -1 times 1. So we can think of the x11 as the input and 1 as the weight, and then we're just doing the same multiplication as before. And we add this up. It's -1 times 1 gives us -1. -1 times -1 is 1, so it adds up to 0. And then -1 times -1 is 1. So the first row we get a value of 1. The second row, 1 plus 1 plus 1 gives us 3. And the third row gets us 1, 1, 1, which is another 3. So that's 3 plus 3 plus 1 gives us an output of 7. Does anyone have any questions about what had happened in the past? Or like this slide in particular? All right, cool.
Sounds really stupid. Can you go through the math again? Like how you got 7? I'm really sorry. I
Yeah,
kind
no, no, no problem. It's like super important to ask questions because like you'll use convolutional neural networks for practically the rest of your lives, and this shit is really cool. So what you're doing is element-wise multiplication. So like we see this -1 is being multiplied with this 1, so it says corresponding value. This -1 is being multiplied with this -1, so this is -1 right here. This is being multiplied here, so that's a 1, and -1 times -1 gives us 1. So we're just adding up the multiplication with this value and its corresponding value in the kernel.
All right, I got it. Yeah, I got it.
All right, cool.
Wait, we do element-wise multiplication and then we add everything on the matrix.
Exactly, yeah.
Okay, cool. Thank you.
Right, and then we keep doing this, right? So we take this kernel and we move it over by 1 pixel. So now it is over here. We take our patch, which is now slightly shifted over, and let's try to calculate this kernel value. So what do you guys think it is? I'll give you some time to calculate it.
Is it 4?
I'm actually not too sure myself.
There's
Let
nine,
me-
right? Like, because there's 9 blocks and there's 5.
5 that are different. Yeah.
How many different? 1, 2, 3, 4, 5. And there's 4 pixels that are still the same. I think it should be negative, right?
Negative, yeah.
Is it
Oh.
like -2?
Wait, what?
Wait, I can't math or anything about this. -1.
Wait, it's
-5
4
plus -5 plus
4
4
minus 5.
Yeah, he's right.
Yeah.
Yeah,
the
so-
the blocks that are different get subtracted, and the blocks that are the same get added. There's 4 blocks that are the same, 5 that are different.
Wait. Isn't it like, so it's 9 and then isn't it just 9 minus 5, which is 4? How do you get -4?
Well,
Dude, no,
because
but-
it's different is 1 times -1. So the sum becomes -1.
Yeah, 1 times -1 is -1. But like, what about the gray times gray?
gray times gray becomes
The gray
positive.
times gray is positive.
Yeah,
1.
so there are more. Oh, I'm stupid. Yeah, that makes sense. I thought,
Yeah, I thought the same thing too.
well,
In this.
all right, got it.
Yeah. So like -1 times 1, -1 plus 2. So that's 1. 0. Then -1, 0. Wait, I got -2. Wait, what happened here? -1, -2. Oh, wait, it's -1. Yeah. So the answer is -1. Now, you can see that the value here is a lot lower. So before it was 7, but now it's only -1. And in fact, we can do this across the entire image. So we can take this kernel, shift it over by a little bit, calculate the new value. So yes, and then we just keep sliding across the image. And each time, once we're at the end, like at this 3x3, let me just go to annotate. This looks pretty cool. I want to try this out. So let's say we go to this 3x3. After we're here, we go to the next line. So it's going to go to here. It's going to keep going. And then it's going to go down. And then keep going. And then so on and so forth. So all we're doing is this translation right here. Does anyone have any questions?
And on the right is like what it would look at the end of it all.
Yeah, exactly. When it's like
I need to move the
there, for example, we'll move over to the next line. It's
So
like
So the dimension of the finalized like grid is 2 minus the original like dimension of the first image, right?
yeah, that is a good, yeah, exactly. That's perfect. I try to sneak that by you because I didn't really want to talk about it, but that's it. You caught that pretty well, and that's a good thing. And that comes down to the problem of padding. You're exactly right, by the way. If we're to do this, the output dimension would be subtracted by 2. So if this was 3, 4, 5, 6, 7, 8, then we subtract by 2, it should be a 6 by 6 output. Well, some of the things we do is we add in padding. So at the sides, for example, we'll just take this image and just put like zeros at the, like along the sides. This way, the final result is going to be the same dimension as it is before. But you don't really need to worry too much about padding. I feel like that's a very miniature step that a lot of people are debating whether you should do padding at all.
So what do you? Okay, well, actually, I won't, that's probably not a relevant question. Never mind.
Sorry, what?
I just had a question about padding, but I guess that's not.
Please go ahead and ask it.
I was going to say, why would you not want to use padding? Because so when you add padding, it makes the dimensions of like the final grid larger. But if you don't add padding, it'll have to be smaller, right?
Yeah, that's actually fine sometimes. And then you look at techniques down the line, we're trying to compress down the image as well. So usually, yeah, you would use padding. But if you really want to reduce your dimension and you don't care about the values along the borders as much, then maybe you don't do any padding at all.
And then when
But
you
that's like a personal choice.
and then when you avoid padding, you're assuming whatever you're looking at. What it like if you want to find the cat is not at the end of the photo.
Yeah, if it's like exactly along the last column of the edge, it like kind of goes away from the image.
Okay, all right, got it. Thank you.
So are all the numbers going to be 1 and -1 always, or could there be other stuff?
Oh, it's going to be completely different. Like it could be 0.5, but I just do 1 and -1 for a very simple example.
Yeah. Also, the numbers are gonna change. You're gonna learn the numbers. So it's like a variable you learn, like in a neural network. A weight.
Yeah, exactly. So the filter is a weight by itself. The filters won't be 1s or -1s. It'll be like 0.5 or something like that. But the key thing to look at here is we look at this filter. It is a diagonal filter. And it turns out if we look at this, it gives us a very diagonal output. Like the values along this diagonal are very, very high compared to everyone else, which is getting absolutely trashed on for getting a score of like 0 or something. So you can see that it's essentially pattern matching. So if you see a diagonal right here, for example, this one matches up with the filter really, really well. Like this right here. It's almost exactly the same as the filter. And we can see that it gets a score of 7 or 8, whatever. It's getting a really high score. And the reason for that is that 1 times 1 will be 1, and -1 times -1 will be 1. So if there's any differences, then the score will get lowered. But if there's more parts that are matching the filter, then the score will be even higher. So especially you see this diagonal will get very high scores since it matches the filter quite well. Whereas values on this diagonal will get scores that are pretty bad because it doesn't match the filter at all. All right, and so now that we have this, and this is something called a feature map, by the way, we can apply what we did before with traditional neural networks. We'll take this output, apply like a ReLU function to it. ReLU is a very popular choice, of course. So why would we not use it? And our next step will be pooling. So this isn't part of neural networks. What it's essentially doing is, let's say our feature map is a 4x4 output. We're going to divide it into 2x2 chunks and then simply find the maximum value in that chunk. So in this case, the value is 20, this is 30, 112, and this is 37, for example. Now, why might we do this, right? Does anyone have any intuition for why we want to try max pooling?
Define objects.
Sorry, what did you say?
Define like individual objects in the image, because the higher the score, right? Because maybe it's not just one kernel, you have like multiple kernels that encompass an object. So you want to pool all those together, and all the places that you pool together probably span the object.
Yeah, so that's a good point as well. We're just taking this image and we can reduce down the dimensionality of the image. Like if we do like a 4x4 image and we keep passing it through the neural network, then the dimension is still going to be pretty high. Like if it's a 64x64 image, the result will be a 64 by 64 like matrix. And oftentimes in convolutional neural networks, you want to like compress down the image. So we look back to this cat example. Maybe like this 2x2 block of pixels doesn't really matter that much because like it's just part of the texture. Or there's 2x2 right here in the background, maybe it doesn't really matter as much. And we can kind of reduce or blur down the image a little bit using this max pooling technique. And oftentimes max pooling is the critical component of a convolutional neural network. If your output of your convolutional neural network is too damn high, then your neural network at the very end is going to struggle a lot. And we'll see that in the future. Does anyone have any?
I have a question. So
Yeah.
The point of it is like you basically ignore areas that you know cannot be like the image you're looking for, right? Because like if there's, right, that's like kind of the purpose of it. You ignore looking at certain areas.
So I think that's like a secondary component. The main component is that it just reduces down the dimension of your image.
Okay, and then let's say the cat is like in the middle of the photo, right? So when you do the max pool, it means that like does that make sense? Like it's not gonna, like when you reduce the dimension, it's only gonna make it, right? Does that make sense what I'm trying to say? Like if you put like a cat in the middle of the photo, and when you do the max pooling, wouldn't that mean that like the value of the cat or like whatever the feature map creates can be split across the 4 quadrants that you made?
I don't think we're pooling like huge chunks of the image together. Like we're only cutting it down by 4.
Oh, this is like for every 16 pixels it does this. It's not like, okay, never mind. Yeah, I get it.
Oh no, it's not divided into like a perfect 4 quadrants. Sorry, I should have made that more clear. It's just a 2x2 chunk. So if we look back to this one, where's our feature map? I don't know where it went. Right there. It would do like 2x2 right here, 2x2 right here. Where's my drawing thing? Yeah, so just.
Yeah, that makes a lot more sense. All right.
Yeah, so just 2, 2, and 2, and so on. Yeah, any more questions? All right, so now we have a full convolutional neural network where we've done convolution, we've done activation, and we've done pooling. And now we have a 64 by 64. Activation doesn't change the dimension. Pooling will reduce the dimension by 2 on both sides and just doing a 2x2 chunk. So it's a 32 by 32. Our output vector is going to be a 1024 vector, which is like pretty all right. You might want to maybe do another pooling to make this like 256, but 1024 will work perfectly in this instance. And now we'll take this vector and we'll pass it into the fully connected layers. And we can now predict classes based on these features. All right, does anyone have any questions about this?
Does the order matter? Like, why does pooling come after activation?
I think if you take activation and you put it after pooling, it should it still work? It will be different, but usually you will see this order, like convolution first, activation, and then pooling. We want to think of convolution and activation as almost like one block by itself, because like with the convolution activation function, you're generating that feature map, and with the pooling, you just want to take that feature map and then reduce the dimension. So oftentimes you'll see pooling at the end.
Okay.
For the collab that you'll be working on today, you could like try switching up the order. If it's all right, let me just check something real quick. How much time do I have? Not a lot. All right, cool. Yeah, so this is our step. We have green is the convolution, red is our like standard technique we worked on before. And we'll do like classification, where it has some final layers, and we run like softmax regression to classify the features. Now, does this solve our issues? Does this solve the problems that we talked about before, where it's not translationally invariant and it is also losing that essential geometry? Does this fix that problem?
I think so.
And why is that?
I mean, because we're actually like considering each and every single part of the image individually. So it's not like geometry. It's not like we're losing geometry because we do inspect every single part of the image equivalently. And again, we're learning the filter. So I think that would probably help recover the geometry part. And then what else were we losing? God, I forgot.
So translational invariant and not we're losing geometry.
Again, I feel like the same thing because the filter keeps moving around, so it accounts for all parts of the image.
Yeah, exactly. So like translational invariant, essentially we take this image, move it over by like pixel, then maybe this column will be gone. And then the corresponding feature column will probably be gone as well. But the feature map still is pretty much exactly as it is before. Like with neural networks, we'll see a drastic change in the hidden layer activations, in the output activation, etc., because like each pixel is now moving to a different input. And so that fixes translationally invariant, and it also fixes the geometrical problem we had before. Since now we're using a 2D kernel for this 2D problem and not using a 1D kernel. So here, we use 2D problems to solve 2D, wait, I said that backwards, 2D solutions to solve 2D problems. Whereas before, neural net was trying to do this in 1D and it's not working at all. Not good. All right, now, one problem that we'll probably run into is, well, we're grayscaling this image, right? So we're turning it into a 16 by 16 image, and we're going to make it grayscale so that it's like between -1 and 1 for each value. Well, what about the RGB channels, right? So our image will be a 16 by 16 by 3 image, 3 denoting the R, G, and B. I don't know why there's 5 of them. I need to fix that. Yeah. So so our image is going to look like that. Well, we can't exactly use the convolution technique as we did before, because this time our kernels will need to look a little bit different. So in this case, let's say our kernel is a 4x4 instead of 3x3 before, just so for extra clarity. So we have this 4x4, and it's also going to have an extra dimension to this. Wait, I can't make that go away, can I? Go away. Shoot. All right, cool. Oh my God. So it's going to be a 4x4 by 3. So now we're essentially taking a chunk out of this image, this 4x4 by 3 chunk, and we're multiplying with that kernel, which is going to be a 4x4 by 3 as well. Does anyone have any questions about that? All right. So just sorry, did someone say something?
Not gonna lie, I did not understand that well. I'm kind of confused still.
Yeah. So essentially we're doing a 4x4. All right, so our kernel is going to be a 4x4, and we're only adding on an extra dimension. So we have 3 right here, right? So it's going to be a 4x4 by 3 patch that we're going to take, and we're going to do element-wise with the kernel, which is also going to be a 4x4 by 3 patch. It's still going to be element-wise, like its corresponding values can be multiplied with this corresponding value in the patch, and we're going to add it all up completely at the end. So we're still left with a scalar value, so that's going to be 16.
Okay, and the 3 is like the RGB part.
The 3 is the RGB part, exactly.
All right, cool.
This is more of a question on, I guess, the previous slide. You said that it like accounts for the problem of like translationally invariant, but it seems like if you translate the input, the feature map will also get translated.
Yeah, that is true. The feature map will be translated a little bit. But the main idea that we want to focus on is that with the neural network, we're sliding over the whole thing. So the feature map is like almost the hidden activation of the network. That feature map will still be roughly the same. Like some of the it will lose some of the edges because the image is slid over, but it will still be very, very similar to what it will look like before any kind of scaling or movement.
Okay. So it
Whereas
looks-
for a neural network, the hidden layer will be like completely different. It's unpredictable if we were to slide it over.
okay, that sounds good.
All right, so let's just go over the whole process real quick. We have CNNs classifying X's and O's. We want to be able to predict quite well that this is X. And we're using these kernels. That looks like that, get a score. Well, right now we're only using one kernel, right? We're just using this like diagonal kernel. That's pretty restricting because then we essentially lose this other diagonal on this X. Maybe we want to keep that when we're trying to classify X's and O's. Well, we can use another kernel. So for example, this other one, we might have like, that looks like this X shape and can help us detect the center. And this extra diagonal right here, that is like this backslash. And that can help us detect the other backslash part of the X. Now, how does that work, right? So we have this 32 by 32 grayscale image. We're using convolution. So, and we have 5 kernels. Well, all we're going to do is that we're just going to take our patch. So this is 3 by 3 patch. We use our kernel, so that's a 3 by 3 kernel as well. We're going to do element-wise multiplication. We're going to do element-wise multiplication, and we're going to get a feature map that's a 32 by 32. Well, now that if we have used like 5 kernels, all we need to do is just stack them on top of each other. Like your output will be a 32 by 32 by 5, where 5 denotes each of your kernels. Does that make sense? Does anyone have any questions? If you're like struggling on any part of this at all, like please ask. All right. And we apply activation and max pull like before. Activation, since ReLU is like an element-wise activation, is exactly the same as before. Or if the value like here on this third kernel was like -2, then the activation will put it at 0. We're using ReLU. And then we'll use max pull. So we divide this into 2 by 2 chunks, just like before. And then just make it a 16 by 16 right now. Anyone have any questions about that? You can, if you have any questions about like further back in the process, then that's totally fine as well. All right, and now we have the 16 by 16 by 5, but we're only using one convolutional layer. So the convolutional layer was that convolution plus activation plus max pull, talked about before as being one layer in the convolution. Well, what if we use a second layer? So we use a second convolution, a second activation, and a second max pull. So we'll take the 16 by 16 by 5, and we'll use 8 kernels, for example. And we can use this little trick before with how we did RGB images by using a, for example, 3 by 3 by 5 patch, where we take this whole chunk of the image, we multiply with the kernel, we get an output. So that will result in one feature map. And then with 8 kernels, we'll get 8 of these. So it's going to result in a 16 by 16 by 8.
Wait, what is the bottom calculation? Like 533, 533 is 16?
Yeah, so this is our element-wise multiplication. Oh my God, this will not go away. I don't know how to make it go away. Whatever. It's essentially doing the same thing we're doing before, where before we had the 3 by 3 patch multiply with the 3 by 3 kernel, we're just adding extra dimension. And the corresponding value of the patch is going to get multiplied with the corresponding value of the kernel. And we're going to add it all up to finally get one value.
Wait, why are we getting like 16 though? Is it?
Oh, 16 is an arbitrary value. Sorry.
Oh,
It,
okay.
It's an arbitrary value. It shouldn't. I can change it to like 25 or something.
Oh, okay.
But that makes more sense. 'Cause I was kind of confused on like the number, like what those like 5 through 3 meant. Right.
Yeah. All right, any more questions? Right. And finally, we can look over this whole thing where we have like 4 convolutional layers. Our input image is going to be a 128 by 128 by 1. So let's say we use 4 kernels. So we're going to result in 64 by 64 by 4 because we're doing max pooling. So first of all, max pooling is going to reduce the dimension by 2. So it's going to become a 64 by 64. And then we have 4 kernels, so that's why it's going to have a 4 at the very end. And we're just going to say our kernels is going to be a 3 by 3, 1 by 1, but that's essentially a 3 by 3. And then our second layer is going to take this 64 by 60 by 4 feature map, and it's going to apply, for example, 7 kernels. Max pooling will reduce the dimension down to 32 by 32, and we have 7 kernels, so the output will be 7. So each kernel dimension is going to be a 3 by 3 by 4, 4 to accommodate for this extra 4 at the very end. And we see this for the next step too. If we use 8 kernels, max pooling reduces it to 16 by 16, and then it's going to be 8. Since we have 8 kernels, we're going to stack the 8 feature maps on top of each other, and we're just going to apply for example, a 5 by 5 kernel instead, with extra 7 to accommodate for the output dimension being 7. Does anyone have any questions about this, about the dimensionality of CNNs? Yeah, Ishan, you can go if you want.
So why do we want to reduce the dimensionality again?
The pure purpose is that with this 128 by 128, that's going to be a very, very high like input. And if we were to continue each time, the result will be a 128 by 128 by 2. And so one way to think about this is that we want this final layer to have a very good understanding of the image overall. And by making this sort of smaller and smaller as we go, this convolutional layer is forced to encode more information into each of these values. So it's able to sort of learn more. Another way of thinking about it is, if we were to just feed this like 128 by 128 by 2 into the fully connected layer, then it's going to have a very, very hard time because the input is going to be so high. It's going to be 128 times 128 as your input vector. Whereas if we were to reduce it down to, what is this? 126, 8 times 8 times 2, which is 128, then the neural networks is going to get a much smaller input, and it's able to accommodate for this a lot better. Like neural networks in general really, really struggle with high dimensional inputs.
So does it have any relationship with like the starting dimensions?
I'm sorry, what?
Like, does it matter about what your starting dimensions are? Like, what if your original picture was like 2000 by like 2000 or something?
Yeah, exactly. Your final convolutional layer will get a different input, which is why you want to make sure all of your images are in the same dimension before you start.
But like, if the image is like a lot bigger in the beginning, like should you always reduce it to some constant like 8 by 8 by 2 or something, or like?
You don't always have to get a 8 by 8 by 2. Like you can do whatever you want, person. Let's say it was like a 6000 by 6000 image, then maybe you add more convolutional layers so that it's reduced even further. Right, any more questions? That was a pretty good one.
Would this generally be like the last layer, or do we apply softmax after this? to get the classification.
So remember, give me 1 second, my computer's dying. So remember that we're taking this convolutional layer, we're going to flatten it down into a 128 vector, and then we're going to pass it to a fully connected layer, and then that's going to get the softmax.
Okay, so we have like a lot of convolutional layers before we actually get into the 1D stuff.
Yeah, exactly. And I will show the whole process, I think at the next slide.
Cool.
Yeah, any more good questions? So next slide. All right, sorry, this is gonna be the slide afterwards where I show the whole process, but I guess what is happening is, so layer one, so layer one gets the input image essentially, and it can detect, and what we'll often see is that layer one will just detect straight lines and curves because it's taking the whole image as input, and it has this very small kernels being slid across the image. So there's not much room that it can do beside like maybe detecting a line or a curve. But now the feature map is going to be a feature map of lines and curves. So then the layer two will take those lines and curves and sort of understand corners and edges from it. And the next layer will detect from those corners and edges, detect circles and triangles. And from circles and triangles, it goes to nose and ears, then bodies and heads, and then finally we detect the entire cap. So each of these kernels are increasing the semantic meaning. And what I mean by semantic meaning is this like higher representation of the image as we move up. As we go further and further up, as we increase in the number of convolutional layers, is learning more and more meaning behind the feature map. And that is something that we'll actually see as well. If we take a neural network that's a convolutional neural network that's been trained, we can see that layer one kernels only detect these like lines and like circles. Layer two kernels take these lines and kind of learn like, we have this circle thing, and then we have like edges and like curves. And this like, you can see that is a lot more information. Whereas layer three, we're starting to detect these like hexagonal shapes, the circles, this like crazy arcs and whatever. And each layer just learning more information and having more value as we move up. Does anyone have any questions about that? So now we get to see the whole process. We're taking our input, we're applying a convolution, then a ReLU, and then maybe a polling, a convolution, then a ReLU, and then a polling. We get back like essentially an image. And we take that image and we're just going to flatten it down into a fully connected layer and flatten it down into a vector, passing to a fully connected layer. And then the fully connected layer will apply a softmax. Any questions about the whole process?
Wait, so we have only one final fully connected layer, or can we have more?
You only have one fully connected layer.
Okay.
Yeah, any more questions? Right, and how do we learn this, learn the kernels? How do we figure out what kernels to use? Well, in the past, they actually hand code the kernels and they were like, okay, so I have this line right here and now we can detect lines. And for the next convolutional layer, maybe we do like a, I don't know, a triangle thing. Oh no, it didn't work well. Well, let's try a circle. Well, that sort of worked well. What about this X shape? Well, that kind of worked better. Why don't we try like a diamond shape? And in the past, it was so tedious and it was like a pain in the ass, essentially. No one wanted to do that. But now we can use backpropagation to learn those kernels. You don't need to know too much about that. We're just going to like do backprop. The math is like a little bit tedious since you're doing like the sum, and it's pretty ugly to look at. If you want to actually implement it, 189 will actually implement it, and I'm sorry, that shit took like 2 years to debug. Yeah. So CNN summary, we have multiple convolutional layers, each of which have a convolution, activation, and a max pooling. We take those multiple convolutional layers, pass into a fully connected layer, output probability labels, and life is good. And now I'm going to go into use cases for CNNs, but does anyone have any like questions about the whole process? I feel like I dumped a lot of information on you guys, so like if you're confused about anything at all, please ask. No one's
So
like
when we do
judging.
pooling, like why do we use max rather than like an average or something?
That's a very good question, and it turns out max just worked better. Like that's it worked empirically better, so everyone used max pooling. There's no good reason for why like you would do max pooling, and people have come up with like intuitive like explanations for it, but it just worked empirically, and that's the reason why we're using max pooling now.
Yeah, I think one intuitive reason I heard is that like you want to select like high features with like a high activation value are sort of like you're really confident that that feature is there, and it's probably like a significant feature you're looking for, so you want to like make sure that you like the existence of that feature goes on to your next layer. Whereas like if you were to take like the min value, like smaller values, small activation values are probably like insignificant. So you want to take like the most significant features at each layer.
Okay, yeah, that makes sense.
Any more questions? All right, so let's look at some use cases real quick in the last 5 minutes we have. So that's going to be, so let's say that you want to actually figure out where the dogs are. And this was like one of our interview questions in the past for recruiting. It was like, if we have like images, how do we generate these bounding boxes around things? So for example, we have YOLO, we can draw a box around this dog, and it should be able to draw a box around this car and say that it's a car and this is a bike. And how it sort of works, just a brief explanation, is that it's dividing the images into these boxes, and each box is going to do a series of predictions. So it makes something that looks like that, and it uses the algorithm to clear out the boxes that have very, very low confidence in. So you can see that the very deep boxes are the ones that's really confident that it has a bike, and it just clears all of them out, and it results in this final detection. And YOLO works super well, and in fact, we can run this in real time as well. So this is a real time, there's a series of techniques going on here, like NanoNets, InceptionNet, faster RCNN, and you can see that it's actually detecting people as they're walking along. And we can also run feature like facial recognition on this as well. So like if you're a big government, maybe this is some sort of technology you want to use. And actually CNN,
I didn't understand how it learned bounding boxes. That confuses me.
yeah, so you're given, so what it's doing is that you're giving an image, and you're given the true bounding boxes. So someone just went in and hand labeled them. There's a series of losses going down, such as it predicts a bounding box. You want to be doing the mean square error to make sure the bounding box prediction is like close by. You want to make sure that the bounding box is very similar in dimension to your other bounding boxes. And we talked about this in our workshop as well, sort of, like the different losses that you would apply in this case to train the algorithm. But I don't really want to go too deep into it. There's a series of papers that you can go ahead and read. It's called YOLO. You can look it up. and it will just work pretty well. And you can actually use CNNs with like natural language too. So for example, if I have weight returning to a vector, and for each of these returning to a vector, well, that sort of looks like an image, right? Because it's a 2D matrix. We can apply convolutional layers to sort of encode the image, and then we apply a fully connected layer. Exactly what we've done before. So we can actually use CNNs beyond computer vision for natural language processing, natural language detection, figuring out from text whether someone is like angry or happy, whether you should buy stocks or sell stocks. Tesla is looking pretty good right now. Maybe you buy some Tesla from what the news articles are saying. Another use is generative adversarial networks. So all of these images, surprisingly, are fake people. And just looking at it, it looks really, really real, right? Like it actually looks like a legitimate person. And even more cool thing that is happening is that you can see that each column, the people kind of are similar. Like, so this woman right here looks like sort of looks like this woman and this woman, like they have the same facial kind of structure. They're looking in the same direction. The only thing different is like their race and their hair color. And also you can see this young boy right here. His race is changing and his hair color is changing as well, but his youth and his like facial structure isn't like changing that much. So GANs can actually learn like how to like model what someone of a certain race will look like, what someone with a certain hair color will look like, what someone looking into a certain direction will sort of look like, and we can disentangle this and make like very, very realistic images. And all these are fake, by the way. And we want to use CycleGANs, which is what I did for a previous project. CycleGANs are really cool. We won't go into how it sort of works, but this is Fortnite. And this is PUBG. And what it's essentially doing, here, Michelle. What it's essentially doing is turning this Fortnite image into PUBG. And you can see that it actually works really well. It's taking out the health bar and replacing it with a gun weapon icon, which is what you see in PUBG. And it's turning the image to be a lot less colorful and Fortnite-y, and making it a lot more like drab and kind of like dark that PUBG has with its very realistic image looks like. And that's the end of the slides. Does anyone have any questions or comments at all? All right, and that's it for our computer vision workshop. There is a IPython notebook that I put in Slack. Go ahead and take a look at it and try coding out some of the stuff. There's like you need to add a CNN, flatten, and use like 2 layers for fully connected. And you need to do the forward pass, but there's a lot of like PyTorch is pretty nice about that. And lastly, you just need to do the loss of the model. What that is. I'll stay in the call, so if you have any questions about coding this workshop up, feel free to ask.
Yeah, I think we can do breakout rooms.
Wait, we're doing breakout rooms?
Yeah.
I got a study for 189. Thank you, Yi. That's good.
Yeah. But how many what's the size of each breakout room that you guys made before?
Maybe probably like 2 and 30 people each.
We'll have like 3 or 4 people.
Oh yeah, we have
So
4 people.
Might as well.
Oh, sorry. All right, it's already linked in the Slack, right? Is this black and white?
Yeah, this is black and white.
Okay.
What are the dimensions of the image?
I'm not completely sure, but you can like print out the dimensions.
Because then like I'm trying to create the layer, right? And I'm using one 2D. Is that what I'm supposed to be using?
Yeah.
Yeah, I'm using conv 2D and it needs like we don't need to give it any like dimensions of the input layer of the
It's 28 by 28.
okay, thank you.
Wait, do the convolution layers return outputs of the same size? Or should we be like counting those sizes as well?
Sorry, what do you mean?
Like if I have a convolution layer which like runs on a 28 by 28 image with like a 3 by 3 kernel,
Mhm.
would the output also be 28 by 28? Or would
I think you can specify same padding just to be safe.
okay. Sounds good.
So what do we set the padding to be?
Adding to what?
I mean, how do we set the padding? What value should we set the padding to?
Oh, you can specify same or a valid padding. So those are the two options, I think.
It's
Let me
I
check real
think we're supposed to supply a number for the padding over here.
Oh, you can do padding mode. Wait, let me just check this.
Are we using maxpool 2D or maxpool 1D? 2D, right?
Yeah, 2D.
I have a question. Why don't we use any hidden activation on the output? Sorry, my bad. Why don't we use activation on the output?
Oh, this is just so that you can pass into a cross entropy loss, something like that.
Cross
can do
right,
like a
cross
soft-
entropy.
Yeah,
Sorry?
you can do like a softmax one.
Wait, it doesn't like does cross entropy loss do softmax for you? Or
I thought it did.
okay.
Yeah, I think it applies softmax for you.
I think we can only max pool it once. Oh wait, yeah, because if we max pool it once, it becomes a fourth of its dimensions, so it becomes 7 by 7. And then after that, we really can't max pool it again.
So for this problem, you can get away with not using max pool if you want, or you can just use only one max pool.
Yeah.
Yeah, I just picked the images to be like a lot smaller, so it wouldn't either kill your laptop or I guess you're running on Colab. Shouldn't be too bad.
Also for Relu, do we just do f.relu? Is that what it is?
Yeah.
Okay. Cool. Yeah, I kind of forgot the syntax.
Oh wow, nice. Oh, Datasys is pretty cool. Wait, just to make sure I used it correctly. Do we have to define is flatten in torch NN?
I'm pretty sure that's the right one.
Okay. Yeah, and we can. Okay, yeah. Damn, I wrote some code and it actually worked like on the, more or less the first try. I was actually training. I'm like, dude, this is like impossible.
Yeah, usually never works on the first try, so that's when you gotta start getting suspicious.
Yeah, that's true. Wait, also one thing, how did you do the loss? Because I did it, I defined the loss outside of, I defined it next to the optimizer, and then I only call loss in the loop.
Yeah, for my solution, I used the f dot negative. I used a different loss with this, but for the cross entropy, you can just define outside.
Oh, okay. You use so you can from what I understand, you either use NN. If you use NN is you define something beforehand, right? And then you use it. And then if we use functional is just you apply it on some input right away.
Yeah.
It's eager execution in TensorFlow.
Yeah.
Okay.
Yeah, I have to go now too, but this was super helpful. I'll finish the notebook. Thank you.
See ya.
Dude, I'm pretty happy we chose PyTorch. That's so clean.
Dude, choosing PyTorch over TensorFlow is one of the best things this club has ever done. TensorFlow is such a mess.
It really is. I remember the cross entropy loss in TensorFlow is so bad. There's 50 different cross entropy losses, and some of them just don't work.
Yeah, and they had 50 different things for their fully connected layers or Com2D. They were switching from their default NN to Slim or something, and then no one used it.
Yeah.
Then you had to use
TensorFlow is Facebook, right? Wait, or am I?
Is it? I know. Is it NVIDIA? I know NVIDIA was
No,
working on it.
TensorFlow is Google.
Oh, what? Google? Oh my god.
God damn it, Google.
And then PyTorch is Facebook.
Yeah.
Oh, it is. Wow. I thought it'd be the other way around. Honestly, I thought TensorFlow seems like it was made at Facebook.
Nah, dude, they're really good at stealing our data. They better be efficient at it.
Yeah, that's true.
Yeah, TensorFlow, I'm pretty sure made by Google because they're kind of bad with customer products for some reason. Do you remember the Google Glass and how people bought it? Everyone threw it away.
Yeah.
For some reason, the products are not very friendly for users. Weird.
Yeah. I don't know. I think I Google Cloud is pretty nice. So Google Cloud is it looks very clean, and there's tutorial videos.
Yeah, as long as it's an API or an online service, then Google does amazing.
Yeah, that's true.
Yo, how do you flatten it? Do you just reshape?
You can do a reshape. You can
Okay.
do like dot view as well.
Oh my, I was looking for an number of epochs. You define it at the very top. Like, where did he put it? After you finish the recording, you want to send it to me, on like Slack, or upload it to Drive and share me the link.
Yeah, I'll put it on YouTube. I'll cut out some of those sections. That would be
Oh,
it.
okay, yeah, for sure. If you do you have the Launchpad channel, of a Launchpad account?
I don't, but I'll send it to you.
Okay, sounds good. Yeah, whatever you want.
Wait, did they change the password at all? If they didn't change it, I'd probably still be able to access it.
It's Moose, whatever.
Let's see. Lexi, are you in bed right now?
Yes. It's nice. I'm doing the Chevin like pose, coding in bed. Yeah, working at home or like remote is it's so easy to just go in bed and fall asleep. It's bad.
Yeah, I did that a couple of times during discussions. Probably like a very, very big mistake because I'm pretty sure they called me out for it.
Yeah,
but I'm not sure.
Dude, during my second project meeting, I fell asleep, and like everybody noticed. So
Oh.
Is this
Yeah.
for Launchpad?
yes, Launchpad. Mokshit was the first one to notice. Like I think they tried pulling me out, and my eyes were closed. I wasn't even in my bed. I was just sitting, and like because like he was addressing the other sub team, and I didn't really give a shit, so I just dozed off.
Damn. Poor Mark.
What? Poor me, man. It was so boring.
True. I added dropout, but I'm not sure if it actually works better. Also, it prints a lot of values, so I can't. Maybe.
Lexi, did
I
you
can't really
did you
see.
find an answer to my question about dropouts?
About what?
Dropouts.
Wait. No. What was your question?
If we're working with regression or something, when we're training a model.
Oh, okay. I got you. Yeah. Wait, actually, you want to ask you this question too? I think it's pretty interesting. I looked it up online, and I didn't see
I
like.
couldn't find an answer.
Yeah. I looked up like magnitude, like dropout changes magnitude, and I couldn't find anything.
Yeah,
What was
They
the
were
question?
just saying never use dropout and stuff. I was like, what the hell?
Yeah, so the question was is like, when you're training dropout, when you're training a neural network with dropout, and your percentage is like your chance of removing a node is like 20%, right? When training like the inputs to the next like node, or just the like all the activations will have a magnitude of like 20% less, right?
Oh,
How do you
Yeah.
and then when you like switch to inference, you're not dropping any nodes anymore, so your magnitude now becomes like larger. And like the question is like, why doesn't that like throw off all your predictions?
Yeah. Hey Alexi, can you show me a notebook? I'm kind of stuck. Like I'm not understanding how to use Comp Duty.
Yeah, you wanna enable screen sharing?
yeah, sure. Give me 1 second.
Oh, actually, if you want to share your screen, I can like. help you
Dude,
out.
my code is horrible. I mean, you can look at it, I
Alright.
feel like crying.
Okay,
Screen sharing
no
is
worries.
yeah.
Uh, uh,
Yeah, that looks pretty good.
nice.
It gets angry. The argument input must be a tensor, not a tuple. Oh wait, am I supposed to do torch start? Okay, wait, let me try that. Let me see if that changes anything. Because for some reason,
Oh yeah.
autocomplete was giving me Comp Duty without me putting an N. So I thought, oh, okay, cool, no need. But let me try it out with.
I think it's also like capital C.
Oh, that's what I thought.
Oh yeah, it's capital C.
No wonder it was working for me with the small c, because it's some other shit.
Yeah. Oh, also, you shouldn't have parentheses around your input and output channels.
Oh,
Those are separate things. Yeah.
yeah, I used to, because like I get confused because like NumPy requires you to do that. Like when you're giving like a dimension, it needs to be all in one argument.
Oh, it's like it's not exactly like a shape, so it's just multiple different arguments.
Yeah, how do I reshape it now? Like if I want to reshape it, what do
I
do?
just did flatten.
I feel like I have
if you just do f dot flatten.
capital F or small f for flatten.
Wait, hold up. Oh, sorry. No. And then dot flatten. You need to initialize it, and then initialize it like and then flatten at the top. Yeah. Capital F. And then you just call it on layer 8, layer 7.
Wait, but I need to give it start dimensions and end dimensions.
I think it works fine without it. It just like flattens everything.
Oh wait, yeah.
Unless
yeah. It's thinking.
nice.
Okay, I think it's happy. Oh damn, I gotta do the rest on my own.
Okay. Yeah. Yeah. It turns out like I guess Torch has conv2d, and then has conv2d, and functional also has conv2d.
Yeah. I got stuck.
Goddamn PyTorch.
You became the thing you swore to destroy.
Yeah. Yo, Alexi, are you coming later tonight to meet like
Yeah,
Frank?
Okay. Yeah. That'll be fun.
Uh, wait, so our final layer has to have a dimension of 10, right?
Yeah.
We count the number of labels. Yeah.
But I haven't applied softmax to the final layer
Yeah.
because you said not to have an output or activation.
So for the loss, you can use like cross entropy loss, and that applies to softmax automatically.
That output of model.
How are your classes going? Wait, what are you taking?
Taking 162, 285, and
Oh,
two
shit.
humanity classes. 162 just like hell on earth right now.
Yeah. Is what are you on in 285?
285, we're going over like actor critic, DQ, and
Oh,
behavior
that's
coding.
nice.
Already like pretty intense already.
Yeah.
But it's coding PyTorch. They just switched over this semester, so I'm super happy about that.
That's nice. Is it wait, who teaches it? Levine?
Yeah, so he Levine. Pretty good.
That's nice. I think he's also gonna teach 182 next semester.
With Levine.
Yeah.
Yeah, I'll probably take that class too, which is a pretty good.
Dude, I think I want to take it too, just because it's Levine.
Yeah, just for the Levine.
Because
What do you
it's
take
also
this year?
like,
Yeah.
I'm doing 170, 188, and 61C.
Oh, yeah.
Yeah. So and then I'm thinking, like 189, 182, and 16B.
Dude, just pass off 16B until like senior year. Why don't you take
Wait.
like 127 or something?
Oh, wait, so you're saying like I don't need 16B for 189? Like,
As long as you know like some degree of linear algebra, you should be fine. Like,
okay.
I think they cover SVD in 16B, so you might need to self-study that. But it's near the end, so it probably won't help with
Oh,
189.
okay. Okay, so wait, what should I take instead of 16B?
127.
Dude, that's what I heard. But
It's the 127 189 Wombo combo. It's great.
dude, the Wombo just get destroyed combo.
Yeah, imagine 182 along with those two classes. I mean, 127, the workload isn't too bad.
Yeah.
It's
Wait,
like
also-
16.
Wait, also I looked at 182, like I looked at the 182 material, and
Mhm.
it's literally just like maybe up to CNNs. It's like our of workshops we teach. You know, obviously it's more theoretical, but like
Yeah.
the topics are all the same. Like I feel like I heard I learned the topics like more or less already. I just I think it'd be pretty cool to be like super solid in the material.
Yeah, I guess. Usually they bring out the like a lot of the deep learning stuff in the spring semester for some reason. So I'm not sure, but there's some other
Yeah.
classes I'll take a look at. That's pretty good as well.
Yeah. Dude, the only thing I'm afraid is if I don't do 16B, I'm gonna be like all by myself in like senior year. Maybe I could take you with some like freshman launchpad members.
Do you know anyone taking it next semester?
I like all my friends.
Oh shit. Yeah,
Yeah.
in that case, yeah, maybe take 16B.
Dude, maybe I just do the 4 technical course.
Oh, ew.
I think not.
I took 4 technicals before, and it was 16B, 61C, and then 16B and 188. But 188 wasn't that much work, and
What? You did all 4?
yeah.
Did you sleep ever?
I was also project leading that semester, so I didn't have a lot of free time. But I still slept at a pretty good hour.
Oh my God.
I mean,
That's
I
crazy.
really like 61C content, so I would just go in and just do it immediately. And 188 really is not a lot of work, and pretty much when you're filling in the to-do sections, it's like pretty easy. I just did it, and a lot of my friends were taking like 16B and 61B, so I just like leached off of them for solutions. It worked pretty well.
Damn.
Damn. He's a leech.
I'm a leech.
No, I totally get the. Wait, what was I gonna say? Oh yeah, 188. It's pretty chill.
No. My
Did you
network,
have a? Wait, what did you say?
my network doesn't seem to be working.
Oh, what's so wrong?
Well, I'll share my screen. Yeah. Given groups equals 1 weight of blah 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 expected to have 28 channels, we'll call 1 channel instead. It's in my forward function, so I've probably designed my model incorrectly.
Can I see your error message again? Huh. And can you go back?
Wait, also your forward never returns anything.
Yeah,
It
I
should
had to
return
return
anything.
My bad.
American. Maybe that was it.
And then no. Also go back up to const2d. The what is it? The first the in channels is 1 because it's a 2D. That's like grayscale image.
So this is 1
Yeah,
comma.
Yeah.
yeah. There's no 28. Like delete one of the 28s. Yeah.
And then okay. So then this will also be 1 comma 28 then.
No, so now it's like you made 28 channels in your CNN1 you made 28 channels. So now you have in the next one you're gonna have 28 channels input.
So it's 28 comma 28. Oh wait. So what is in
Yeah.
channels? What is in channels supposed to mean?
It's like the the third dimension. It's like your image is 28 by 28 by 1. And then you have like you apply multiple kernels. That's like in this one you have 28 kernels
In
on
the
each
first-
const2d. Both.
Okay, so no, I don't get how it's 128 and then the next one is 28 comma 28.
So your image is like 28 by 28 by 1, right? Then you apply the const2d, and the XY might change, but now you're gonna have 28 channels. And then like
What is the channel?
channels like you have it's the third dimension in your image in general. And when you have multiple channels, it means like you have multiple kernels.
Okay, cool. That makes sense. Because wait, so are we assuming 1 kernel per channel?
Yeah. So to get like for every channel in your output, you have like 1 kernel.
Okay, that makes sense.
Right. E.
Fine. Let me see if that. Oops. What did I do? Oh, comma.
I think your flat end might be wrong too. Well, actually, we'll see. Because my linear had a lot more units. I think your linear is gonna have like a lot more input.
I'm max two.
That's wrong. Wait, I don't know what is the 2?
2 is the number of. Wait, I forgot what it was. It was the. Wait, what? Oh no, I just
Oh
read
yeah. Kernel size is fine. I think. It's your conf2d is not gonna be the next one. Is gonna be still gonna be 28 for the instead of 14.
The first one?
Yeah. So the conf like max pool does not decrease the number of channels. It only decreases x and y.
Oh, fuck. Right. So then this would be.
And then it's gonna be like I don't know what the number is, to be honest.
28 into 28.
Oh, 28 cubed, maybe.
Yeah. So 21,009.
Big number. Did you do that in your head?
No. What the fuck?
Okay, just wondering.
I mean, it's Launchpad. I wouldn't be too surprised. Oh. What is this?
What is? Oh, add matrix.
Dimension 1 is an as matrix, 2 dimension 0. Let me just output what the hell I get here. Oh wait.
I don't think you get anything. It crashes in the middle. Okay. Your dimensions are fucked now. All right, go back. Inspector Gadget. Oh, it's gonna be 14, because after max pool, your x and y is 14, so it's gonna be 14 squared times 28. No, you don't have to change that. No. Go conf2d is still like 28.
Right. That makes sense.
And now your torch linear, it's gonna be like, yeah.
Hold up, let me calculate that. Oh, it'll just be divided
Also,
by.
you can also just plug in 14 times 14 times like.
Oh yeah. Python knows math. I forgot about that.
Wait, are you sure that's right?
I divided it by 2.
You should divide it by 4 because your x and y both change.
You said 28 by. Does it become 28 by 14, or does it become 28 by 14 by 14?
So okay, let's start. So your input is 28, 21, right? Then it becomes 28, 28, 28. Then it's still like after the next quantity is still 28, 28, 28. Then you max pull it, so it becomes 14, 14, 28. And then you apply another quantity, so it's still 14, 14, 28. And then you flatten it, so it's like 14 times 14 times 28 by 1.
Okay.
Yeah, so yeah, that should be fine. Psych. Okay. Oh, that crashed.
It fucked up there. Argument size must be a tuple of ints.
Oh, it's you do the floor division.
No, floor division.
Do like 2, yeah.
Target and input must have the same number of elements. Target.
Okay, it failed the loss now. Oh wait, go down. So you're calculating loss on data and out. It should be loss on target or loss on output and target, right? Because your loss is not on the data. Yeah.
Shit. That was really dumb. Okay.
That's all right. No worries.
Fine. Nope.
Output, target.
The dimension of my output.
Should be fine. Yeah, do a little output dot shape or something.
Oh yeah, shape, my bad. 64,
Yeah, it
10.
looks right.
That's fucked. That's fucked. 64, 10. Why is it 64, 10?
Because it's a batch size of 64, I think.
Okay. Oh,
Um,
okay, it does 64.
yeah,
Alright.
you can also print target dot shape.
Yeah. Yeah.
Oh, what the
Single?
fuck? I think you need
Aren't
to
they
use a
tables?
yeah. It's like a number like 0 to 10 or
Oh,
0 to 9.
Yeah, because it's one.
So
Oh,
you need
we
to
one hot coded.
yeah
We one hot coded.
yeah you need to use a different loss function. I think.
What do we do?
There's one called nn dot cross entropy loss.
Okay. Fuck yeah. Oh no. Oh no, it's printing the fucking thing again and again. Shit.
Well, I think it works. It's printing is
Well-
probably training.
Let me get rid of this.
Oh yeah.
Okay. Wait, so what is it showing? What are these? Oh, these are the data.
Yeah, it's like our prediction.
Trouser. Whoa. Whoa. Loss. The loss is getting lesser. Okay, that's nice.
Yeah.
My God.
Oh, I think it looks pretty accurate.
Yeah, it is getting
now.
better.
Yeah.
Add drop into your model by using neural network.
Okay, I'm gonna go.
Yeah,
I
I'll do
have
this
something at
later.
4.
As well.
Oh
Alright,
yeah,
cool.
yeah.
Thanks
I mean,
for
looks,
joining, guys.
you're pretty
Bye-bye.
close, yeah.
Yeah, I am reasonably close. All right,
Yeah.
thank you. Bye-bye.
All right, it was a good workshopy. I'll see you later. Oh, I'll see you. Oh fuck! I spilled water. Oh no. Sorry. I was gonna say I will see you tomorrow.
See you.
Oh my
Wait,
God.
are you not coming tonight to retreat?
Oh, yes, I am. I will see you tonight. Actually.
All right, see you tonight, bro.
Okay. Bye.